Ok, bonjour à tous. Donc, bienvenue à cette nouvelle session des Scientific Talks du vendredi. Merci de m'avoir proposé pour gérer cette session. Donc, je suis Rémi Dubois. Donc, c'est une session qui est orientée valorisation et start-up de l'IHU. Donc, c'est aujourd'hui avec plaisir qu'on va entendre deux des spin-offs de l'IHU présenter leur thématique. Alors, vous savez sûrement que il y a eu pas mal de spin-offs qui sont sortis de l'IHU. C'était un des piliers forts de l'IHU, pouvoir valoriser la recherche. Alors, peut-être en deux mots, je peux vous rappeler quelques noms. Il y a une start-up qui marche très bien maintenant, qui est en fait antérieure à l'IHU, donc elle est moins associée à l'IHU, mais qui s'appelle Fine Art, qui marche très bien, qui fait une pompe cardiaque, qui est maintenant installée à Pessac derrière. Donc, eux, ils ont une pompe d'assistance. Et donc là, ils ont levé beaucoup. Ils vont faire leur first in man bientôt. Là, donc, c'est vraiment une belle réussite. Pour ceux qui étaient là il y a longtemps, alors je ne sais pas laquelle a été créée la première, mais il y a eu OP2. Donc, bon, OP2 qui a été une histoire sur un médicament. Donc, on sait que c'est difficile. Le repositionnement d'un médicament existant. Donc, malheureusement, OP2 n'a pas survécu. Mais donc, c'est quand même la dure réalité pour certaines startups. Donc après, on a eu Inart qui continue. Alors Inart ne présente pas aujourd'hui parce que vous connaissez sûrement beaucoup mieux Inart que les deux startups qui présentent aujourd'hui. Donc Pulsar Certis qui présente. Et puis là, on a deux nouvelles startups qui sont dans les tuyaux. Donc il y a BioValve Therapeutics que vous ne connaissez pas forcément, mais qui va être porté par François Roberti et Jean-Benoît Tombeau qui fait des biovalves imprimés. Donc ça, c'est quelque chose qui est en train d'être monté. Et Olva Medical, une start-up dans laquelle j'ai le plaisir de participer, qui fait on révolutionne le business du cathéter. Voilà. Rien que ça, on aura l'occasion de nous présenter un peu mieux, mais en tout cas, on essaie de faire quelque chose de la medtech qui soit plus sustainable que ce qui est fait aujourd'hui, c'est-à-dire tout en single use et des cathéters qui traversent 3 fois le monde avant d'arriver devant le patient. Donc, aujourd'hui, c'est donc Pulsar qui va commencer, donc la plus jeune start-up créée, on va dire, de l'IHU. Et donc, Michael, je te laisse présenter ça pour de bien.
Bonjour à tous. Est-ce qu'il y a des gens qui ne comprennent pas français et que, enfin, do somebody speak French? Everybody speak French, or should I do it in English? Okay. English is better. Okay, let's do it in English then. Thank you, Laura, for your good advice. I will do it for our next talk. So I'm really honored to be here today to present you the startup where I'm involved. I'm Michael. So there's people here also from the startup. So I will...
de Pulsar peuvent se montrer là, comme ça, ceux qui sont de près ou de loin impliqués dans Pulsar, voilà, qu'on s'identifie tous. Donc moi, je lève la main aussi. Voilà, donc voilà, Pulsar, voilà, donc comme ça vous saurez maintenant que vous les croiserez à la cafétéria pour dire merci, excuse-moi de t'avoir.
So yeah, Pulsar is a startup which was founded in December 2022, and it's incubated here at Lyric. And the main goal is to transfer the excellence of the academic research from Lyric and other international partners to the market for the benefits of patients all around the world. And maybe specifically, the goal will be to develop a ready-to-market, non-invasive medtech system to clinically predict the risk of sudden cardiac death. So actual approaches to predict this risk of sudden cardiac death are first genotyping, which concerns a subset of sudden cardiac death. So it's around 10 to 20%. And there is actually some inconvenience because there is a lot of different gene variants, and it's pretty complex to evaluate the functional outcome of these genes. The second approach will be, it's actually the structural imaging, which is really accurate to detect the scars and other structural abnormalities in the heart. but it's only for structural heart diseases, and it's quite expensive for, let's say, emerging countries. So there is a third one, which is the electrical phenotyping, which is fast and quite cheap, and it also pretty easy to use in daily routine for screening of the whole population, let's say. But the thing is, there's a need for more developments to be effective. And at Pulsart, the horse that we choose is the electrical phenotyping. Oh, sorry. Electrical phenotyping. And so the talk today will be just around this electrical phenotyping, and especially about the signal processing that we are performing at Pulsart actually. So I will talk about our approach. First, I will talk about the hardware, then the database that we will work on, and the signal processing aspects that we are working on. So first, to give you an idea of where we were when we started, there is a lot of known ECG markers for sudden cardiac death. So there is markers for depolarization aspect of the signal, and the repolarization also. There's other markers. And usually, well, for example, we can average the signal and have an average beat from which we will extract the late potentials. And it's something that maybe some of you already saw before with, for instance, on the top, it's a late potential of a sick patient, where you see that the late activity is quite long compared to a healthy volunteer. And regarding the repolarization markers, there is one which is really classically used, which is TPIC-TN. And this is, let's say, our basis features that we are, with which we started our work. And the main goal, the idea of the project will be to record the signals with a high resolution EKG, then do the whole signal processing aspect, and from this signal processing, extract some features that will be used in a classification model, for instance, or other machine learning techniques, let's say data sciences, from which we'll extract a risk stratification score. So yes, let's first talk about the hardware. So it's a Biosemi system which contains 128 electrodes with 1,018 on the chest and 10 on the back. The recordings are all long, around 10 minutes. And there's also a respiration belt for the respiratory signal, which is used for the signal averaging. Usually we, the signals and all the features can be visualized in a graphical user interface that was mainly, or I think entirely designed by Georges, which is here in the audience. So here we can see this 128 electrodes. Then we can also see the whole average beats in each of which comes from each lead. Here, for instance, we can reproduce the position of V1, V2, V3, V4, V5, V6, for instance, and put some markers. Here it's the QRS markers. And then if we want to specifically visualize one lead, we can have this in black, this average beat from the lead 100, and all the beats that we selected to do this median beat, actually. So yeah, so this is mainly what we are using to visualize the data from Biosemi. well, where come the data? So it's for the moment we are mainly using data from here, but we will have a multi-center acquisition from other centers from France, for instance, Rennes, Paris, Toulouse, but also from Vietnam and Thailand. So for the moment, we have around 100 subjects acquired from the hospital and the institute. And it's the distribution of the arrhythmia diseases are like something like this, with a huge part of the patients with an ischemic cardiomyopathy. And we have also it's an issue to define patients that are not arrhythmic, and actually there's also another issue, which is what is the distribution in the population of non-arrhythmic versus arrhythmic, and it looks like our data is not really representative of this, and it can be maybe a problem for our classification models, but it's just to say, like, we have some distributions that are quite interesting. Now about the signal processing and the feature extraction. So first, as all the feature processing step, it's the pre-processing. So we have to exclude the bad leads, as you can see here on the right, with the 128 electrodes that are overlapped here. And you see that the green ones looks pretty good with an PQRST, but the red one is really bad. So these ones will be excluded. So it can be done manually or automatically. We also have sometimes a real issue with external high frequency noise. It can be at the hospital or also here. So depending on the environment, and for this maybe we will need a Faraday cage, but it's an ongoing discussion. And we also observe for the majority of the data a huge baseline drift, as you can see here, and we develop already some techniques to correct this. So yeah, it was some few steps that we perform for the pre-processing aspect. Then we can perform an signal averaging approach. So we have an average bit, as you can see here, and we can put easily the markers of the QRS and the T wave. And we can also, so we can do all the signal segmentation approach that are relevant for clinical features. And then we can also extract spectral features and other features that can be relevant to study a fragmented signal. As you can see here, it's quite fragmented signal from a patient, and we can have this kind of representation in our graphical user interface quite easily. We also extract features from the vectorcardiogram or VCG. So it can be features as QRS loop, area, or planarity. So there's a huge amount of features here also. We also did a bit-to-bit analysis. So we can extract heart rate variability features, and that we usually represent like this, with different kind of plots that represent how the heart rate varies over the time. And we also have the QTM, which is a normalization of the QT interval bit to bit, and the period repolarization dynamic, or PRD, which is, as its name indicates, I'd say it's related to the T wave. We also have the opportunity to study the body surface features. So first, we can just visualize. That's one thing which is really interesting for some cases. Can either visualize by displaying the extreme values, the highest ones and the lowest ones. But we can also, let's say, interpolate all the values and represent it as a heat map. and observe that, for instance, for this healthy volunteer, we have a completely different pattern than for this patient. And the idea is then to study the topography of the features and also the distribution to extract some relevant features of the that can predict the sudden cardiac death, or at least the arrhythmia. So all these features extracted make a huge amount of features. And so we can imagine at least 4 different ways to reduce this huge amount of features, starting by reducing time by averaging, for instance, or starting by reducing in space, so reduce the number of leads, for instance. And then we can also reduce the number of features by selecting the most relevant for different types of pathologies or arrhythmias. So we can do this combination at least in 4 different manners. So this is something that we are investigating right now. And this will allow us to do a machine learning model, which will be hopefully really robust, from which we will be able to construct a sudden cardiac death risk stratification score. And so the idea is quite simple. It's to have features going to a classification model, and then from this model, get the prediction and construct a score with this. And it's actually a work that was already done here really recently by Nolwenn Tan during her PhD, and she already imagined a quite interesting approach to do this in this manner. And so now one of our ongoing work is to replicate this work on a bigger database and hopefully obtain better results, but she already have a really promising results. So yeah. So to conclude, the idea of the startup is to use ECG approaches, and especially the signal processing of the ECG to develop a risk stratification score for sudden cardiac death. And so for this, we need a high resolution, also high quality signal recordings, an interest in good development of the signal processing aspect that we will use, that will provide some features that we will use in data science, and maybe also some additional data will be to obtain some recordings from some dynamic recordings, for instance, during sport or other types of let's say external stimulation. So yeah, so that's it for me. Thank you.
Thank you for the presentation. Any question ou des questions en français, en English? Ouais.
Hi, thanks. Really interesting talk. Questions more about the startup itself, and perhaps it's a question also for Remy in that case. So could you just clarify what was the individual major advancement? What is the innovative part of the project, and what major advancement made you decide, okay, now we're going to create a startup on this?
Okay, so good question. There are several answers. So first, we had this work from Nolwenn Tan. So at the end of our PhD thesis, we had some results claiming that we were able to discriminate patients that are more likely to do VF based on the score based on the surface ECG. At the same time, Michel did had some result from patients where in which he measured directly on the epicardial side of the heart with the catheter the signals for patients that had idiopathic VF. And he observed that for these patients, we have some fragmented signals. And these fragmented signals were not associated to structural disease that we can measure with standard imaging. So it means that there is something on the heart that is abnormal that we cannot measure with standard imaging. And these fragmented signals is a kind of trace of something that is related to these abnormalities. And the assumption was that we at some point we will be able to measure this fragmented signal on the surface. So that's why we have all this system with high resolution ECG, multiple electrode, because we do know that this signal exists at least in some patients, and we want to be able to measure this abnormal signal on the surface. So to answer the question, two things: first, with encouraging results, plus the intuition that we will be able to get these features on the surface. And if you want to add comments,
Okay.
You're after the holy grail of electrocardiology, I think, and people have been working on this problem for several decades. So why do you think that you will succeed where others have not? I assume you have an answer to that, but it's not a cynical question.
So there is, I can answer maybe. Yeah. So there is a major part that we discussed, just mentioned at the end of the talk, is also the pacing. So pacing is important because we observed that when you pace the heart, you have a different propagation on the heart, and you know that it can reveal some abnormalities on the heart. And so today, when you do an ECG, it's a non-invasive test. So you observe the heart with the standard or normal propagation. But if you pace the heart in different locations, you have different propagation, and you can reveal some abnormalities. So measuring high quality here, ECG, and stressing the heart with different pacing will probably reveal things that we were not able to measure before. So the non-invasive pacing is something that is very important in the process. So on one side, you have the electrical measurements with the system, and on the other side, you have how to stress the heart in order to reveal things that are not that you cannot measure at baseline, probably. So that's maybe where there is some part for us, room for improvement.
Maybe you should also watch the Monty Python movie where they are looking for the Holy Grail, especially the end, because it turns out that the French have it.
Moi, j'avais juste une question. Donc, c'est une start-up. Est-ce que vous allez créer un produit derrière ça? Et si oui, quel type de produit vous voulez créer, mettre sur le marché?
C'est peut-être le but de la start-up, c'est de au moins développer un produit qui sera directement prêt à mettre sur le marché. Et donc, pour ça, on a eu justement cette semaine énormément de discussions sur les différentes normes qu'il faut respecter et sur comment avoir un produit qui peut être assez facile d'utilisation, qui peut être réutilisable aussi. Donc, disons que le but, c'est de faire assez vite pour l'avoir. C'est limite, c'est littéralement, je crois qu'on s'est donné 4 ans pour avoir quelque chose qui sera mis sur le marché directement. Ah oui, pardon, le type de produit, donc c'est une veste dans laquelle il y aura les électrodes pour enregistrer le signal. Et il y aura donc ça c'est de la partie hardware, il y aura aussi sûrement avec un prototype, enfin pas un prototype, on appelle ça un transduceur pour PC. Et on aura à côté un aspect software qui permettra de faire donc l'analyse du signal et de enfin alors est-ce que ce sera juste analysé, ce sera au médecin de regarder les fissures et de décider, ou est-ce que ce sera carrément comme une boîte noire où on met les signaux et il sort le diagnostic? Ça, c'est à définir encore, mais je partirais plus sur cette deuxième option-là. Donc, c'est quelque chose dans ce style.
Peut-être juste pour compléter, donc l'objectif, c'est la stratification du risque en population générale. Donc c'est quelque chose sur lequel donc ça veut dire que c'est un outil qui doit être utilisable dans le meilleur des cas, donc de toute façon chez un cardiologue, et dans le meilleur des cas, chez le cardiologue de ville. Voilà. Donc idéalement, on arrive à avoir un outil qui arrive jusqu'au cardiologue de ville. Après, il va y avoir quelques contraintes parce que si effectivement, comme on disait, si on veut stresser le cœur avec du pacing, on peut techniquement le faire enfin, il faut avoir l'environnement technique. Il pourrait y avoir une première version effectivement de stratification du risque qui passerait que par les signaux avec le rythme normaux. Et puis après, si on passe à certains seuils, on passerait sur le pacing en milieu plus clinique, plus hospitalier. Mais donc le produit, c'est bien ça, c'est quand même quelque chose qui est fait pour la stratification en population générale, l'objectif final. Donc c'est un système qui soit relativement simple d'utilisation. Mais donc là, effectivement, on est sur des échelles de temps assez longues. Hein. C'est dans la medtech, 4 ans. Bon, on verra, on en discutera avec Certis juste après, mais c'est long, quoi. Questions? D'autres? Any questions? Bon, merci. On va passer.
Okay, so I'll continue in English too. So hello everyone, Xavier Riobé. I will talk about Certis Therapeutics. So we are working on a product to address thermal ablation. So thermal ablation usually is the aim is to burn cells, so typically tumoral cells, but you can still be interested because there are also some applications for the heart, for example, to kill cells that will disrupt electrical flow in the heart. So at some point of the company, we will also address the heart issues. But for now, we are more focusing on burning tumoral tissues, so either in, for example, in the liver or in the prostate, but it can be many organs in the body. It can be the brain or anything else. So the main principle is to apply some energy to hit the cells and to end up killing them. So it's something that is already done in the hospitals, but for now they are missing the monitoring part. Some companies already do it, but we'll see later how we are doing it better. So why we need some monitoring about these ablations? Because there are two risks. Either we do not burn all the tumoral part, so there are some parts left. That implies that the cancer will go back again, and then it will be even harder to treat it. Or on the opposite, we can also burn too much tissues and burn tissues that are healthy and that we want to preserve, and it can become very dangerous if we touch some other organs that are close to the lesion we want to ablate. So to monitor that, there are many devices. It can be ultrasound, fluoroscopy, CT or MRI. And our idea is to use the MRI to do that. Why? First, because there is a better contrast in the images. so we can see smaller lesions than with other modalities. Of course, there are no radiation compared to the CT, for example. So we can also mention some positive aspects of other devices, like, for example, ultrasound, that are easier to for positioning the ablation device. But we can also do it with the MRI, and MRI manufacturers are now working on this topic too. So we will be soon able to also position the device with the MRI. The current drawback of using the MRI is the availability of MRIs in the hospitals, because they are mainly used for diagnostics, especially in France. But same thing, it's already starting to shift, and many hospitals now have dedicated MRIs for interventional radio treatments. And with some of them, we could not do some thermometry monitoring, for example, fluoroscopy or CT. We can do it with ultrasounds, but it's way more precise, accurate. So that's why we choose to use the MRI. So why Certis is here? So first, it started in 2018, end of the year. It started from research from Bruno Caisson team here. So it was at the beginning trying to address thermometry monitoring in the heart. So even if now with the company we start with other organs, we will at some point go back to the heart. So some people of the company that you will recognize, so of course Bruno Caisson, Valérie Ozen is participating too. Pierre Bourg has now joined the company. So as it has been mentioned before, to go from the research results to a product, it needs some work. So for us, for example, it took 3 years to have the first product. And we need to have different competencies in the team. So not only researchers to develop the project, but there are also a big part of, for example, regulatory issues to address, and even for the development itself of the software. So, for example, myself, I'm come from a dental imaging industry, so not related to heart, but the processes of developing a product are similar in the end. So we need to put in place some procedures to follow the software development, to be sure that the product in the end is pretty robust, because we don't want to have any issues during an intervention. So it starts with research, and then it goes toward developing a commercial product. But we are still doing research, of course, and we'll talk about that at the end of this presentation. So if we talk about our product, so basically we have a computer installed in the MRI console room that's connected to the MRI. So the interventional radiologist inserts a heating device that can be either microwaves or radiofrequency, can be laser or ultrasounds. So while once the heating device is inserted in the patient, we start scanning the images about it. So both anatomical images to see, for example, if you talk about the liver, so to see where the liver is placed and the device inserted on it. And then with the different signals of the MRI, we can process them to generate some heating maps, temperature maps, that the interventional radiologist could see in real time. So in the end, it looks like that. So the software. So maybe first I have to precise that first the product is the software, but we are also working on MRI sequences to have a faster acquisition, for example. And we are also working on developing some heating devices. So we'll start with a laser, but we can then work with many other ones. So the software, once it's connected to the MRI, so it starts receiving all the images. So here is just a gel, but after I will show you some real cases about liver tumors and prostate tumors. It's like a classic imaging, medical imaging software. We have a part here with different orientations of 2D views, axial, sagittal, coronal, and a 3D view here. On the left, we have some parameter options, and we can place some points close to the heating to monitor the temperature itself, so to see the temperature elevation. So the software is compatible with both 1.5 and 3T magnetic fields. We are compatible with all heating devices. And when we talk about real time, we talk about 10 slices every second. So we can really see almost in real time the effect of the temperature. So we have 4 main steps in the software. So the first one will be the planification. So we can do, for example, registration if the patient already had CT scans before with some segmentations on it, or we can do segmentation on the acquisition from the MRI too. We can position our temperature landmarks to have different places in the organ or in the tumor we want to monitor the temperature from. Then we have second part. The user will set up its acquisition, like where he wants to have the slices, which orientation. Then the monitoring by itself. And in the end, after the procedure, we have some post-ablation tools to see if the dose coverage is enough for the initial target or not. So I can show you an example here. It's a liver with microwave. So you can see here the temperature map increasing around the microwave probe. And here we see it in 3D. So it's accelerated. And you can see here the graphs of the temperature rising. And I can show you. So, for example, the big plus of our solution is that in real time you can see where the heating is diffusing, and if it's going, for example, in this case, if the tumor was closer to the dome of the liver, if the temperature rises too strongly, too highly, close to the dome, it could hurt the patient. The user can see at every second where is the temperature rising and if he has to stop or not. I have another example here. It's for the prostate. So we have here we are monitoring 3 temperature points, but we will see here. So in all the directions, you see the heating increasing. So here it's with a laser. So we have 2 fibers, if I remember well, inserted, and it creates a bigger ablation zone. This part here is the rectum. So we don't want to hit this part. It could be dangerous for a patient. So with our solution, we can clearly see in real time how this heat will approach this place that we want to keep intact. And so the user can stop the heating when he sees that the temperature goes too close to this part here. While without our solution, currently they're just, they insert the fibers and they just follow the laser or microwave devices constructor table saying, oh, if you want to have a lesion of 3 centimeters, you have to burn for, let's say, 5 minutes at this energy level. And but they cannot know during the procedure if the temperature is going way more further than they predicted or if it's not enough. So why our solution is, we think it's better than current ones. For example, the current ones only have 3 slices, so it doesn't cover the full lesion. And they only get the information every 8 seconds or 10 seconds, depends on the companies. While we can cover the full lesion and having the information every second. And we can have the full 3D view of it. So there are different companies working with different ablation types, but usually they are only focusing on one therapy, one clinical target, while with our solution we can address different ones. So even for the hospital, it's better to have only one product addressing the different issues. And we have better imaging performances. So for now, we're working, of course, with the IHU Lyric, where we do our tests, where we do clinical trials with animals here. We have some projects with CHU Bordeaux. We already have many dozens of patients treated in Munich Hospital for the liver. And we have started last year with for the prostate at Radboud in the Netherlands. We are arriving to 10 patients now. And we are working with other research hospitals like Mayo Clinic in the US or Stanford Hospital. And soon we will work more with French hospitals and other German ones. So this is for current projects, but we are also continuing the research. So I can talk a little bit about that. So we have 2 PhD students here currently at the IHU. So we have Manon, who's working to do some retro control of the temperature for the ablation. So for now, it's the user that press the button to deliver the energy. But we are working on an automatic procedure where the software controls also the heating device. So the user can select the temperature he wants to reach. And depending on the images that we will receive and compute, we can decide if we need to raise the temperature, the energy, or lower it. So we have performed many experiments already here on some pigs and with our software using a laser device, the one that we are developing. Yeah, so 2 examples. We could choose to set different thresholds to increase the temperature in different steps. And software will automatically control the device to reach this threshold, hit at for some minutes at this threshold, go to the second one, etc. Or just set one, and he will keep the temperature as needed. We are also working, as I said, on different laser techniques. So instead of having only one fiber, or that we have to use multiple fibers, so it's longer to insert and everything to obtain different shapes instead of just a sphere. We can have one fiber with different outputs or control at the same time multiple fibers. So you can see here a small video. This is just for one fiber. So if we use that, we obtain a shape like a sphere. But we can also have, with one single fiber, multi-directions. So here we can hit here, then it will heal all around the fiber. So with that, and we can decide if we want to light just on one part or not. So we can obtain shapes that matches more the target lesion. And we also have Fanny Dabrin, who's working with HiFuse to obtain same kind of results, but with another technology. But they both already have presented their work here, so I will stop here. Thank you. If you have any questions.
Thank you. Thank you for the presentation. Any question? Audience? Maybe I can start with one question. You discussed about your clinical partners. And so it means that you already have a solution that you sell to this partner, or is it a clinical trial that you are doing now?
So up to last year, it was just for clinical trials, but now we have a product that we can sell to any hospital that would want it. So we are, if we talk a little bit about regulatory, I don't know if everyone is aware, but there are different levels for medical devices. So for now we have level 1 medical device, and for next year we are applying for level 2.
To be probably. So
yeah, to be.
Right.
Yeah.
Because you are only, so for those who don't know, there is 3 levels for regulatory, 1, 2, and 3. And level 1 is when you are completely outside the patient and you don't make any decision.
Yeah, it's related to the risk for the patient. So if there's a risk of death, it's the highest level, it's level 3. If there are absolutely no risk, it's level 1. And if there is a risk of injury, it's level 2.
And the
to make
reason
it
why
simple,
you're going to change is because you are going to control the therapy. So that's why you need switch.
So level 1 was the idea was to have a first product so the user can use the information, but it's not the only information he has to use. So he has to rely on different informations. Level 2, now we can say that, yes, if on the software we are saying that you are heating there while you don't want to, stop the heating. Or if it's not heat enough, you have to continue. Yeah. And level 3 will be when the software will control the device and decide by itself if he has to turn the power on or off. Mm.
Other questions? Yeah.
A question. Thank you for this presentation. I was wondering, so I understand the software part of your development. Do you also plan to one day commercialize the tools for delivering the lesion with some laser and ultrasound solutions? Is that correct?
Yes, we are working now to develop our own laser. So it's the last part I was showing. So to be able to have a more complex heating, like shape of the heating, and instead of having to use 2 or 3 different probes to obtain different shapes, with maybe with one we can achieve it.
Okay, and it's a device that would be specifically linked to your software so that it can be controlled by the software, but could it be also a standalone device?
Yeah, so it could be used directly if the user controls it. So if he turns the power on off for every source of energy, but the idea is to have it as a full package with the software controlling it.
Very interesting. And do you have any partnership for developing the heating device, or do you do it yourself?
For now, the prototype we work with the Alphanov, who's in Pessac.
Yeah.
And we are thinking then for the moment where we will have to produce it, maybe with other partners. Yeah, not really decided yet.
Thank you very much. Well done.
Thank you.
Okay, look, see, it's about the versatility of the approach to track the ablation temperature, elevation and temperature. So you show that there's 4 modalities to generate ablations that you can track. I'm wondering if we can add another one. I'm curious to know if your temperature monitoring can also track temperature losses as well as temperature elevation.
Yeah. So
cryoablation.
yeah, you're talking about cryoablation. So for now, the algorithms we use are only applicable for increase of temperature, like high temperature. We can not use it straight away for cryoablation, but it's something at some point we may work on it and integrate in the software too. Yeah. For now, it's just heating, but the software is already thought to be able to someday integrate cryoablation too.